atoms don't exist in isolation in most substances. They bond together to form compounds. But how they bond depends on their electron configurations, especially the electrons in their outermost shell, known as valence electrons. Atoms are more stable when their valence shell is full, usually with 8 electrons, known as the octet rule. To achieve this, atoms either transfer electrons or share them, giving rise to 2 major types of chemical bonds: ionic bonding and covalent bonding. Ionic bonding happens when one atom gives away 1 or more electrons to another atom. This usually happens between metals and nonmetals. Metals, like sodium, Na, have only 1 or 2 electrons in their outer shell. It's much easier for them to lose these electrons and empty their outermost shell, revealing a full shell underneath. When sodium loses 1 electron, it becomes a positively charged ion called cations. On the other hand, nonmetals like chlorine, Cl, have 7 valence electrons and need just 1 more to reach 8. So they are eager to gain electrons. When chlorine gains 1 electron, it becomes a negatively charged ion called anions. Now we have a positive ion and a negative ion. Opposites attract, and a strong electrostatic force pulls them together, forming an ionic bond. This is how common table salt, sodium chloride, NaCl, is formed. In an ionic compound, electrons are not shared but transferred. The result is a crystal lattice, a repeating pattern of ions. These compounds usually have high melting and boiling points. They conduct electricity when dissolved in water or melted because the ions are free to move. While ionic bonds involve a complete electron transfer, covalent bonding is about sharing electrons between atoms. This type of bonding usually occurs between 2 nonmetals, which both need to gain electrons to reach a full valence shell. Since neither wants to give up electrons, they agree to share them instead. Take water, H₂O, as an example. Hydrogen has 1 electron and needs 1 more to have a full shell, which, for hydrogen, means 2 electrons. Oxygen has 6 valence electrons and needs 2 more to reach 8. Each hydrogen shares 1 electron with oxygen, and oxygen shares 1 back, forming 2 single covalent bonds. In covalent bonding, atoms share 1 pair of electrons, single bond, 2 pairs, double bond, or 3 pairs, triple bond. Molecules may be polar, like water with uneven sharing, or nonpolar, like O2 or CH4 with equal sharing. Covalent compounds usually have low melting and boiling points. They don't conduct electricity in water, and they exist as molecules, not crystal lattices. The main difference between ionic and covalent bonding is in how the electrons are handled. In ionic bond, electrons are transferred from one atom to another, creating ions that attract, whereas in covalent bond, electrons are shared between atoms to achieve full outer shells. Understanding these bonding types helps explain why salt dissolves in water, why water is a liquid, and why some substances conduct electricity while others don't. Now that we understand how atoms bond, either by transferring or sharing electrons, the next question is, how do we represent that on paper? That's where Lewis dot structures come in. Lewis dot structures are simple diagrams that help us visualize how atoms bond by showing only the valence electrons, the outermost electrons involved in bonding. These diagrams are a key tool for understanding covalent molecules, where atoms share electrons to achieve stability. Drawing them becomes easy once you learn a consistent step-by-step method. To draw a Lewis structure, follow these 5 key steps. First, count the total number of valence electrons in the molecule. Use the periodic table. Group numbers usually tell you how many valence electrons each atom has. For example, oxygen has 6 and hydrogen has 1. Second, identify the central atom, which is usually the one that appears only once in the formula and is less electronegative. Hydrogen is never placed in the center. Third, connect each surrounding atom to the central atom using single bonds. Each bond represents a shared pair of electrons, so draw a line between the atoms to show that. Fourth, distribute the remaining electrons as lone pairs, starting with the outer atoms, so that each atom, except hydrogen, follows the octet rule, having 8 electrons around it. Once the outer atoms are satisfied, place any leftover electrons on the central atom. Finally, if the central atom still doesn't have a full octet, you may need to form double or triple bonds by converting lone pairs from surrounding atoms into bonding pairs. This step helps the central atom reach stability. Let's look at a simple example: carbon dioxide, CO2. Carbon has 4 valence electrons, and each oxygen has 6. That gives us a total of 16 valence electrons. Carbon goes in the center, with an oxygen on either side. We start with 2 single bonds, 1 to each oxygen. Next, we complete the octets of the oxygens by adding lone pairs. But now carbon has only 4 electrons from the 2 single bonds. It needs more. So we turn 1 lone pair from each oxygen into a double bond, and we get the final structure with all atoms now having complete octets. Now let's take a slightly more complex molecule: sulfur dioxide, SO2. This one can be tricky for students, but it's a great example of why Lewis structures matter. Sulfur has 6 valence electrons, and each oxygen also has 6. That's 18 valence electrons in total. Sulfur goes in the center and bonds to both oxygens with single bonds. After placing lone pairs on both oxygens to satisfy their octets, we'll have only 2 electrons left, which we place on sulfur. But sulfur still doesn't have a full octet. It has only 6 electrons so far. To fix this, we create a double bond between sulfur and one of the oxygens by using one of oxygen's lone pairs. That gives sulfur 8 electrons. But here's the interesting part. We can do this with either oxygen, so we actually get 2 valid structures. These are called resonance structures. The real molecule is not just one or the other. It's a resonance hybrid, a blend of both. Also, notice that sulfur ends up with more than 8 electrons in some versions. That's okay here, because sulfur is in period 3 of the periodic table, which means it can expand its octet using available d orbitals. This is something only elements in the 3rd period or beyond can do. In summary, Lewis dot structures help us understand how atoms bond and share electrons. Start by counting electrons, building single bonds, completing octets, and adjusting for double or triple bonds when necessary. While simple molecules follow clean rules, more complex ones, like SO2, introduce concepts like resonance and expanded octets. But with consistent practice, even the difficult ones become manageable and logical. If this helped you understand chemical bonding, give the video a like and subscribe for more easy explanations in science.